Uh, Good morning, all. I will start the class in a minute. Okay, so once again, we'll begin our session with a small recap of what's been taken the last week. Lectures 26, 27, and 28 were talked about the system models. In the book, by Bolton, these three lectures is part of a single chapter, and therefore I've also kept them together here. So essentially, a, there are a few types of actuation systems like mechanical and electrical, hydraulic and pneumatic, and all of these, though fundamentally different, it's fantastic to know that all of them have very similar governing equations. The entire lessons of 26, 27, and 28 talk about how to form the governing equations and how to mathematically model these equations. In case of mechanical, we have springs, dampers, and masses, and we normally write the equations using the Newton's laws of motion. In addition to the springs, dampers, and masses, we also have the rotational counterparts. For example, rotational springs, rotational dampers, and moment of inertia. And in this case, the Euler equations are slightly more relevant. Additionally, we also consider the concept of power and energy for all kinds of systems. Electrical systems have inductors, resistors, and capacitors, and we have learned the equations of these before, but in these lessons, we more or less related it to the mechanical equations and showed the similarity between these. Finally, we also have hydraulic and pneumatic systems, and these systems didn't have particular specific names I would like to write. So, and it's more like the equations turned out to be very similar to those of mechanical, electrical systems. Now, all of these modeling is then used for the lectures 29, where we studied about the dynamic response. In the dynamic response of a system, given the governing equation, we try to solve it in different ways. We first saw about first order systems and second order systems, and then we try to solve it in the sense of having the total response as a sum of transient and steady state response. Transient by definition means a short term response. Transient means brief or ephemeral. Steady means the long term response. After this, we concluded the lecture 29 by talking about performance measures like delay time, rise time, and the like. Lecture 30 is quite mathematically intensive, and we'll be solving a couple of questions from lecture 30. Lecture 30 talks about transfer functions, frequency response, and a body plot. So, to study transfer functions, it is very important to properly learn about the Laplace transform, and we'll solve a couple of questions based on Laplace transform soon in this class. From Laplace transform, a very natural step is to study the frequency response. That is, since we know that sines and cosines are related by a derivative and also a phase change, it is possible to write every differential equations in terms of sign, and as in every variable will be a sine omega t, and when you simplify the expressions we'll get another magnitude and a phase change. To frequency response and Laplace transform, or in general the transfer function, gives us tells us one of the simplest way to analyze the stability of the system, and that's using the Bode plots. So that concludes a recap. Is there any specific questions about any of the lessons? If there are, we can see that first and then move on to my the other questions I've written down. Okay, if there are none, we'll just so I'll give you a few minutes for you to solve this. You just have to write the governing equations, and by governing equation in this case all of these will be differential equations. So I just need to see the differential equation which governs the two cases. I will give you 3 to 4 minutes on this. In case the things are not clear, there is an input of Q here, and this is H1 and this is H2. So let's consider the first question. So in the first tank we have an input of Q, and there's a flow from the first tank to the second tank, and this depends on the pressures. Given in the lecture slides, we know that we have the resistive elements of the hydraulic system, and the equations of that is as follows. Where P1 is the pressure in the source, P2 is the pressure in the sink, Q is the flow, and R is the resistance. So we know that the pressure in the source here was rho g H1. The pressure in the sink is rho g H2. And that is equal to Q into R. Therefore, the flow from tank 1 to tank 2 is as follows. The equation of okay, I'll include the area. The equations of the first tank will be Q. The rate of change of volume in for the first tank is Q minus Q, because this is the input. So there is no letter here actually. That's just that. and this one is H1, and this one is H2. Sorry, I just read the message now. So the rate of change of the fluid will be so, and that is equal to the volume, rate of change of the volume. So that will give us, yeah, likewise for the second tank, we'll get Q is equal to A2H2 dot. We can naturally substitute this back into the equations, and we'll get so this gives us a coupled set of equations, and we can solve these simultaneously to get so these will be the governing equations of this system. And did that make sense? Okay, so similarly we'll do the next question. So we have, I hope this for this question everything is visible. Okay, yeah, this is Vn. So if you write the equations again, say there is current I1 here, and I2 here. So the first equation we'll write is, sorry, I mean we have current I1 in this branch and current, so that implies that the current in this branch is I1 minus I2. This is from Kirchhoff's current law. So if you write the, say we have grounded this, and this is at Vn, there, okay, the voltage here, okay, let's call the, okay, I'll just write the equation just like that. Okay, So V in, V out. Okay. Anyways, the main point is we have three coupled equations and a couple of variables to go to match with it, and therefore this is the system. We this is the these are the equations of the system. So if I had to, in usually what we will do is we'll rewrite this system as d by dt of I1 minus d by dt of I2 into R2 is equal to I2 into C. Yeah, is equal to I2 into C. And we also have V in minus V out is equal to I1 into R1. So here we have two equations and two variables and a coupled set of a coupled equation, and therefore this is the model of the system. Did it make sense how I wrote these equations? This equation I've just written by, we know that V out is the potential across the capacitor. The potential, because this capacitor is in parallel with the resistor R2, that means the potential across the capacitor is the potential across the resistor as well. So we have V out is equal to the potential difference across the resistor. We know the potential difference across the resistor is the current multiplied by resistance, and that's what I've written. Likewise, the potential across the capacitor is Q multiplied by C, where Q is the charge on the capacitor. Therefore, we have this equation. The charge on the capacitor Q relates to the current flowing through it through this equation, naturally, because current is the flow of charge. So the derivative of Q will be I2. So I'm taking this equation and taking a derivative of it with respect to time. And on taking the derivative, when you take a derivative on both sides, the derivative of I1 is d by dt of I1. Derivative of I2 is d by dt of I2. Derivative of resistance is a constant, and some likewise derivative on the the right side of the equation is I2 into C. So that is how you can note that the point of these exercises is to just form the equations. We have learned how to solve it in the lecture 29, and when I'm going through that lecture 29 part, we'll see how to solve these kind of equations. So similarly, these are two more questions. I think I should make this bigger. Theta 1 is the orientation of the first gear. Theta 2 is the orientation of the load and the second gear. The motor applies a torque of T1. C1 is the damping. C2 is also the damping. I's are the moment of inertia. So when you're solving this, naturally the first part is to write the, if let's consider the first gear. The first gear has two torques acting on it, the torque from the motor and the torque from the other gear. We know that every force has an equal and opposite reaction. Thank you, Newton, for that. So that means the force at this boundary has to be equal and opposite. Therefore, the torque at this boundary won't be equal and opposite, because torque is equal to force times radius. So by the properties of by the properties of gears, we know that N1 by N2 is equal to R1 by R2. So since the forces are the same, the torques between the gears will also be T1 by yeah. We'll just call this ratio as N for convenience. So that is T1 is the torque that the first gear applies on the second gear, and T2 is the torque the second gear applies on the first gear. So if you write the equations, the torques on the system are, the torque for the first gear is T minus T2. We have damping also, so minus C1 theta 1 dot, and that is equal to the inertia of theta 1 double dot. Likewise, we have T1 is equal to that is, if you are looking at the equations on the second gear, T1 minus C2 into T2 dot is equal to I2 into T2 dot. I2 into theta 2 double dot. We also have this relationship, so the equation simplifies to give me a second. Oh, in addition to these, we have one more equation I had forgotten. We have to assume that the power transferred due to the torque at the center has to be the same. So that gives us equation T1 theta 1 dot is equal to T2 theta 2 dot. That is because the first is the power is the power due to the first gear, and second is the power due to the second gear. So this gives us another equation in terms of to solve for T1. Oh no. I will come back to this in a while because I feel like I've made a small mistake somewhere. I will. Now, can you solve this question now? I hope this question is visible. I can write it bigger. So personally, whenever I come across these kind of questions, like as in what the undamped frequency is, I always relate it to the mechanical system of equations because I'm more familiar with the mechanical system of equation. The mechanical system of equation, we have m a m x double dot plus p. The undamped frequency, by definition, in case of the mechanical system, is root k by m. That is the coefficient of x, and we care about the coefficient of x and the coefficient of m. Therefore, in this case, we should look at this term and this term. Therefore, the undamped frequency would be 4. I hope that made sense. So, for the undamped frequency and the damping ratio, for these, it's necessary that you remember the equations. For example, the equation of the. Give me a second. The definition of damping ratio, which is this absolutely ugly variable, is C by 2 root mk. Yeah. So if you are for the same question, we'll just substitute the values. C is 10 and 2 root mk is square root multiplied by square root of 16. So that's like 1.25. From this, it will be kind of evident that this is a overdamped system, and because it's an overdamped system, the one way to simply solve this is to just know this solution, know the general solution and substitute the values. So if you look at the general solution, you will get, in the case of overdamped, the equation we get is okay, wait, before that, we know the solution is the transient solution plus steady state. For steady state, we solve it by equating the thing to 0. So that is, we take this equation and have write. Give me a second. Yeah, for transient, we equate it to 0. So if you're equating a transient to 0, we'll get these terms from the equation: a e to the power s1t plus a b e to the power s2t, and for the force response, we have to do it specifically for each question. In this case, when you do the force response, we'll get that when you're solving it, we'll just get that I is equal to 1, because if you have, oh no, not this. If you have d2 by dt2 plus 10 di by dt plus 16I is equal to 16, then we can assume the solution that I is a constant. And if we assume the solution I is equal to constant, we have these two terms to disappear, and and when that happens, we naturally get k is equal to 1. So the force response is k is equal to 1. So for this, it's plus 1. S1 and S2 are terms which depend on what the are terms that depend on oh no, I've forgotten the pronunciation of this letter. Zeta, sorry, yeah. So S1 and S2 depend on so in the equations we have, yeah, in the class notes we have S1 is equal to minus zeta omega n plus omega n into square root of zeta squared minus 1, and S2 is the same but with a minus sign here instead. But this is the boring way of solving the question, and I much rather prefer solving it properly. So if you are going to solve it properly, let's write the question down again. So in general, the premise to start these questions is to assume that the solution is a e to the power st. We start off like this because we know that we can see that all of these terms have the derivative of all these terms will preserve the e to the power st, and that makes the simplification of this equation quite convenient. So this following equation will become a s square e to the power st plus 10a s e to the power st plus 16a e to the power st is equal to 0. Since it's known that e to the power st is never 0, we now have a quadratic equation to solve. A s square plus 10as plus 16a, the a's also cancel, is equal to 0. When you this means that s is equal to minus b plus or minus. So we have s1 is equal to minus 2 and s2 is equal to minus 8. Now, given the initial values of this question, because this is a second order differential equation, we require there would have been two constants of integration on integration. So we should have two boundary conditions. So say we had started with I of 0 is equal to 0 and I of d I by dt of 0 is equal to 0. Then our final equation will be, we have S so this means that I is equal to we have two linear equations and two variables to solve for A2, A1 and A2. The solution to this is trivially A1 is equal to A2 is equal to 0. But say if any of these were one or something else, then we will have to work a little harder to solve it. I hope this made sense. But anyway, the point is we have S1 and S2 to be minus 2 and minus 8. So when you substitute this into this equation, given initial conditions, we can solve for A and B, and therefore we have the solution to the equation. Did that make sense? Okay. Now another way we could have solved this. Okay, we'll solve this question also. For this question, all you're expected to do is know the equation. This is given in the notes. In the part of the performance metrics, in the part of the performance metrics in the dynamic system responses, we have these terms. So that question will just be a plug and chug. So the equation in this case is e to the power this will be the value and then u. Yeah. We will solve this question again using transfer functions later. Likewise, they can ask what's the maximum percent, what's the rise time and things of that sort. And the equations for those are also given. Note that for the rise time in the slides, they have given the 100% rise time. We had this discussion a while back, essentially because there are multiple types of rise time, and we usually have to specify what percentage you are trying to reach. For example, there's a 90% rise time, that is the time taken for the input to reach 90% of the output and things like that. So in the question in the slides, the rise time given is for the 100% rise time. Anyways, we'll move on to finding the transfer functions, or in this case the gain function. Yeah, the I will just copy it from the slide. Yeah, this thing. I hope now it's visible. Yeah. So did anybody find the transfer function for the first question? Okay, looking at Sir's slide, I have used a slightly different convention. I'm using y as the output and x as the input. The transfer function is always defined as g is output by input. So yeah, in the slides, Sir has written x to be the output and y to be the input. I didn't notice. Yeah. So on taking the Laplace transform of this, we get s square into y of s plus 16s into y of s plus 5y of s is equal to 10x of s. That means taking y as common, we get s square plus 16s plus 5 is equal to 10x of s. Therefore, we get y of s by x of s, which is the gain, is equal to 10 by s square plus 16s plus 5. I hope that made sense. So can you likewise do the second question? So in the same steps, we're taking a Laplace transform of the entire thing, we'll get 7s square y y of s plus 5s y of s plus 3, this dot is not supposed to have been here, 3 y of s is equal to minus s x of s plus x of s. Taking x of s common in the right hand side and y of s in the right, we get y of s multiplied by 7s square plus 5s plus 3 is equal to x of s minus x plus 1. Remember, g of s is output by input, and output is y of s, input is x of s, so we want y of s by x of s, and that gives us 1 minus s by 7s square plus 5s plus 3. I hope that made sense. So now we'll solve a couple of questions on Laplace transforms. Like, in general, whenever you are solving questions on Laplace transform and which have Laplace transforms, you always have this table, because like it's firstly not expected that you memorize each of these, but some of these are just common enough that you kind of eventually do memorize. This is quite important. This is quite important. This is quite important, and this is quite important. And likewise, this is important, and these two are important, and so is this. In some classes, this is also talked about a little. It's a very useful property if you're actually solving it, because if you look at it, like this one, I'll use a different color. A few other properties is a direct application of this and the things you have already seen before. And another very important thing to do about when you're solving these questions is practicing how to do partial fraction decomposition, because that's very convenient. So is there we'll solve one of these right now. Like, by definition, the Laplace transform is integral of 0 to infinity e to the power st into f of t dt. So let's do the Laplace transform of e to the power at. I think I've missed a minus sign. Yeah, there's a minus sign here. Yeah. The integral of this will be and you're evaluating the integral at 0 to infinity, so that gives us at 0 the multiplied by t. Yeah, at 0 the numerator is 1, so we'll get numerator is 1, at infinity the numerator is 0, so we'll get Yeah, provided a is positive. So that means we get this is equal to 1 by s minus a, which is as expected. Likewise, this property integral of minus is from 0 to infinity of e to the power minus st f prime of t dt. For this question, we start off by, to simplify this, we start off by using the product rule for integration. So say u is equal to e to the power minus st, dv is f prime of t dt. That means du is equal to e to the power minus st minus s dt, and v is f of t. The product rule gives us uv f of t into e to the power minus st evaluated from 0 to infinity minus integral of v du. In this case will be f of t multiplied by minus s e to the power minus st dt. On evaluating this, on evaluating the first term, we get f of 0 multiplied by 1. Sorry, I missed a minus sign. Oh, I didn't miss a minus sign. Never mind. So we'll get f of infinity into e to the power minus s into infinity, and this is 0 because e to this second term is 0, minus f of 0 into e to the power 0, e to the power 0, minus, we take this minus outside the integral and therefore that becomes plus, so we get plus s, because s is a constant with respect to t. S does not depend on t. So we integral f of t e to the power minus st dt. So but we know that this is the definition of Laplace transform. So here we get s into f of s minus f of 0, and that is exactly what we have here. So the important thing is you can do the same thing for f double prime and likewise for any higher order terms. Now let's try solving this equation with the Laplace transform. I hope I'm not moving too fast. These make sense. I'll take that as a yes. So if you're taking a Laplace transform of this, we get s square I of s plus 10s I of s plus 16 I of s is equal to 0. Sorry, I meant we'll solve this, so it's equal to 16. So that gives us I of s is equal to 16 by s square plus 10s plus 16. And now we can simply do a partial fraction decomposition. So in general, the steps, if you know remember the equation, you can find the inverse Laplace transform of this directly. But in general what we do is we use partial fraction decomposition to write this in terms of its factors. So we know the denominator is s plus 8 into s plus 2, and this is equal to k1 by s plus 8 plus k2 by s plus 2. This is the premise of partial fraction decomposition. That is, if you can factorize the denominator, you can write the rational function in terms of the as a sum of the factor denominators. So in the specific steps to do this is to take this equation and expand it. So that means k1 into s plus 2 plus k2 into s plus 8 divided by s square plus 10s plus 16 is equal to 16 by s square plus 10s plus 16. I hope that these parts made sense, how I've added these terms. Now I can simplify the numerator of this. So that gives us s into k1 plus k2 plus 2k1 plus 8k2 by the denominator. Now if this is equal to this, the only way that's possible is if 16 is equal to s into k1 plus k2 plus 2k1 plus 8k2. But this is a function in s. If a function in s has to equal a constant, that means this term k1 plus k2 has to equal to 0. Essentially, we are saying that there's a plus 0s here. Two polynomials are only equal if each of their coefficients are equal. So if 16 plus 0s is equal to 2k1 plus 8k2 into plus s of k1 s multiplied by k1 plus k2, that means s of k1 plus k2 must be mapped to 0 multiplied by s, and that means k1 plus k2 is equal to 0, and likewise 2k1 plus 8k2 is equal to 16. This allows you to solve for what k1 and k2 are. In this case, it will probably be really ugly. k1 plus 4k2 is equal to 8. k1 is equal to minus k2. So k2 is equal to 8 by 3. Yeah. So that means the partial fraction decomposition of this is k1 is k2 is 8 by 3. So k1 is minus 8 by 3 into s plus 8, and k2 is 8 by 3 into s plus 2. So and we know how to take the inverse Laplace transform of these two terms. The inverse Laplace transform of these two terms will relate to e to the power at, and so the coefficients, so we'll get I of s, I of t is the inverse Laplace transform of this. So it's minus 8 by 3 into e to the power minus 8t plus 8 by 3 into e to the power minus 2t. If you notice one thing, the Laplace transform method gave us the same set of equations we had here. So naturally it would be right, and I personally feel a Laplace transform method is much nicer and more elegant than the other solution, and then doing this method. So I wanted this class to also show you which are the better methods to use essentially. Are there any more questions on how I did this? Yes, partial fractions are a very convenient way to help out in solving for inverse Laplace transforms and stuff. Especially because in the Laplace transform has this very fantastic property that can convert differential equations to algebraic equations. And on top of that, not only are these algebraic equations, these are also algebraic equations with rational fractions, rational functions. If you have a rational function, you can take the partial fraction decomposition of it, and that makes things much simpler to solve. Yeah. Additionally, like what I've shown right now is like the not so elegant way of doing partial fraction decomposition, and there are more fantastic ways of doing partial fraction decomposition which are kind of easier, but explaining why those works requires knowledge of complex analysis, which is a little too above my pay grade. So yeah, so we can solve another question of this form. So let's take yeah. So for instance, had this been a step input, sorry, instead of a step input, had this been a ramp input, then we would have a give me a second. I have made a very careless mistake. So the Laplace transform of 16 is 16 by s. That means the I of s is by s, and we'll have one more term in the Laplace transform. So I feel this is a prime time that you try solving this for 5 or 10 minutes. In the meantime, I'll drink water and come back. So, did anyone solve? Okay, we'll solve it by hand now. So on simplifying this, on rewriting this, we get k1 into s1 plus s plus 2 into s plus k2 into s plus 8 into s s plus k3 into s plus 8 into s plus 2 is equal to 16. Now, one of the easier ways to solve this is, because we know this function is true for any value of s, we can generate equations by taking specific values of s. So if I take s is equal to 2, s is equal to minus 2, if s is equal to minus 2, this term disappears and this term disappears. And therefore we'll get 16 is equal to k2 s plus 8. S is minus 2, so 6 into minus 2. That gives us k2 is equal to 16, 8, 3. 4 by 3. If you say s is equal to 0, the first term disappears and the second term disappears. So we get 16 is equal to k3 into 8 into 2. So into 16. So that gives us k3 as 1. Likewise, if s is equal to 8, minus 8, the second term disappears and the last term disappears. So we get 16 is equal to minus 6 into minus 8, and that simplifies into k1, and that simplifies into minus 1 by 3. So now we have the three partial fractions, that is I of s is equal to minus 1 by 3 into 1 by s plus 8 plus minus 4 by 3 into 1 by s plus 2 plus k3 by s. K3 is 1 by s. And therefore, when you take the partial fraction, if you take the inverse Laplace now, which is very trivial, we get minus 1 by 3 into e to the power minus 8t plus minus 4 by 3 into e to the power minus 2t. And we just saw that the Laplace transform of 16 is 16 by s. So inverse Laplace transform of 1 by s is 1. Yeah. The previous solution we got would have been the solution to I'll just write. Would have been the solution to this. Where this is the Dirac delta function. Sorry. Is it Dirac delta or Kronecker delta? Give me a second. Yeah, it's a Dirac delta function. the Dirac delta function is defined as 0 everywhere, but at the value it's defined as 0 everywhere, but at 0 it evaluates to infinity, but in such a way that integral of Dirac delta dt is equal to 1. Anyways, that's not necessary for this discussion. So if you're learning more about signals, you'll come across the Dirac delta in a few ways. It's a very useful concept. Now I said I'll solve this question. I've done that, and essentially even all of these equations can also be likewise solved using the Laplace transform, and but except that the equations will just be slightly longer to solve. Okay, and then the next thing sir had done was about frequency response. For frequency response, wait, is there any questions to the way sir had done anything? Like, I'm not particular. The phasor representation is useful, but I just personally feel like the transfer function method is superior, and therefore I'm not very keen on solving questions on those. However, the concept of Bode plots are quite useful. Bode plots also allow you to find ways to know when the system is stable and unstable. I was not looking forward to solving Bode plot questions though. Okay, but we'll do it nevertheless. So now we'll solve a question on Bode plots. So for Bode plot, we first start with the transfer function g of s, and though it was not explicitly mentioned, the transfer functions are functions in the complex plane. So the value s can take complex valued terms. If you're keen enough, you'd notice that the definition of the Laplace transform is very similar to the Fourier transform. In fact, it differs by a I term in the exponential. And that is essentially the premise. We are going to look at g of I omega, or rather g of j omega, because we use j I for many variables. So let's say we have a simple transfer function g of s is equal to 1 by 1 plus tau s. That means g of j omega is 1 by 1 plus j tau omega. Since it's a complex valued function, this essentially has two parts to it. This has the magnitude and the argument. Like for example, the magnitude of 1 plus I is root 2, and the argument is pi by 4. So the concept of Bode plots is that we plot the argument and the magnitude and argument of g omega as a function of omega. So we must first find the magnitude and argument. The magnitude of g omega we can write this as 1 plus j tau omega to the power minus 1. That means the r, the yeah, and the magnitude of this is 1 by square root of 1 plus omega tau square omega squared. Did that make sense? Now when you're plotting the magnitude for body plots, we do something kind of special. We have the x-axis of the body plot is a log scale. That is, every term differs by a factor of 10. So we have 1, 10, 100, minus 0, 0.1, 0.01, and so on. This is the why we do this will be clear in a while. Additionally, we do not really plot mod of g omega. We actually plot my 20 log 10 of mod g of j omega. This has a very this is motivated because most of the transfer functions we have are products and sums of things we know. For example, we'll have a couple of terms in the denominator, couple of terms in the numerator, and all of these are multiplied by each other. We very rarely come across a transfer function which is of the form g of s is equal to s plus sin s. We never come across things like this. So, by taking a log, we are able to split apart the big transfer function into multiple smaller transfer functions, and that makes it very easy to plot each of these. So if you take 20 log 10 of this, we'll get 10 log 10 of 1 plus gamma squared omega squared. For simplicity for this diagram, I'll take tau as 1. We'll take tau as 1. So if you take a small value of omega, that is, as it tends to 0, we have this tending to 0, because we have 10 log 10, 1 plus a really small number, which is 10 log 10 of 1. Log of 1 is 0. So we'll have our plot will be very close to 0. Oh, there I made a small mistake. So it's a minus sign because this is in a denominator. Now, as omega becomes really large, 1 plus omega squared is very close to omega squared. So we'll get minus 20 log 10 of omega. So as if omega is really large, so say after 10, the slope is minus 20. And to connect the graph at this part, we'll just connect it like that. So the body plot of g of s is equal to 1 by tau s, 1 by 1 plus tau s will be something like this, except for tau it will be centered around tau. Did that part make sense, or should I go Should I explain this again? Oh, just to clarify, this is the magnitude section, and we have not yet looked at the argument section yet. I am audible, right? Oh yeah, okay. Okay, so for the argument section, we'll do a similar analysis. For simplicity, let's consider for simplicity, let's consider 1 by 1 plus. Let's take gamma equal to 1. If gamma is let's take tau equal to 1. So that means the g of j omega is 1 by 1 plus j omega, and we want the argument of this. If omega is really small, okay, instead of this transfer function, let's consider a transfer function g2 of s is equal to 1 plus tau s, and setting tau is equal to 1, we'll see g2 of j omega. So this gives us 1 plus j omega. Now if omega is really small, then this term is dominated by 1, and therefore the argument of this term is very close to 0. So if I draw the graph, the argument, it'll start off very. So once again, this is a log. So we have 1, 0.1, 0.01, 10, 100. So if omega is really small, the argument is 0. If omega increases, as omega becomes larger than 1, naturally the argument will be closer to pi by 2. I hope that's reasonable. So this is pi by 4 and this is pi by 2. So if let's say omega is like 10, it has reached pi by 2, and in between we know when omega is equal to 1, it will be 1 plus j, and there the argument is pi by 4. So this is how the thing will look like. Now if you think a little, it's kind of easy to understand why g of s is equal to 1 by 1 plus tau s. If the Bode plot of this will be the exact opposite. Oh. So the easier way to explain to argue for this will be the argument is also okay. So in the case of the magnitude, we took 10 log 10, 20 log 10, so that the product in the g of j omega is nicely resolved. In the argument, the product of g of j omega is already nicely resolved. The If I take two complex numbers a and b, the product a multiplied by b, the argument of a multiplied by b is argument of a plus argument of b. The argument of a complex number is already resolved in this way. We do not have to take a log to for the nice properties of thing for the thing to pop up. Now we know that g2 of s multiplied by g1 of s is equal to 0. Oh, sorry, is equal to 1, where this is g1. The argument of 1 is 0 for any value of s. So if I'm we just found the argument of g2 to be up. Since argument of a multiplied by b is argument of a plus argument of b, the only way from this equation, it's pretty clear that wrong pen. Like, yeah, I hope that kind of makes sense. It's a little hand wavy, but it's the premise of the thing. So say there are multiple. So say you have a transfer function which is 1 by 1 plus 10s and multiplied by 1 plus 20s. So the steps to solve these questions would be to first draw the Bode plots of 1 plus 10s, which in this case will be 1, so 1, 10, 100, I'll use a different color, so it will be from 10 and the for the frequency stuff we have 10 here, so pi by yeah, and likewise the same the Bode plot for 1 plus 20s in this case will be slightly shifted, and therefore it will be very similar. And here also will be okay. Instead of 20s, we'll just put 50s because that look more realistic. And once you have drawn the two Bode plots, you add the two plots, and therefore what you'll get in this thing will be a slightly a steeper graph for the magnitude and a graph which goes like that for the argument. Similarly, if you have things in the numerator also, so say it's 1 plus 5s by everything, you will just include that in the thing in the equations as well, so it will be like that and 5, so and then when you add, you have to add this plot also to the graph. That's the premise of Bode plot. There's two more things in Bode plot which are kind of useful. Like, but Sir has not said that in the slides yet. Essentially, Bode plots can also be used for relative control. Sorry, relative stability. That is for closed loop systems and the like. And that's not written here, so I do not know if I should touch it right now. So the main reason these transfer function method is so powerful is because the thing we have learned in the, which I mentioned already in the first class, block diagrams. Block diagrams are so conducive to studying how the transfer functions work together, because transfer functions are multiplicative. Even though normal algebraic equations or normal differential equations for the different blocks are usually differential equations and not very nice equations, in for if you move from the time domain to the S domain, everything's an algebraic equation. So if you have an input x. So normally we look at this in terms of time. So we have x of t, and then we have y of t here, and we'll measure some value from using the some measurement thing, and we get some signal here. We subtract the signal, and on subtracting a signal we take the result from subtraction, up, give it to the particular controller and actuator, and that gives us the output. But all of these are all differential equations. But the moment you move to the S domain, everything just becomes a product, and that makes it very convenient. So if you have y of s here, after the measurement, here we have h multiplied by y, because by definition the transfer function is output by input. So the input to this h is y, so the output is h multiplied by y. So this signal is the difference of this. So we'll call this E for error. E is equal to x minus h into y. So the input to the controller and actuator is this signal, which is x multiplied by h into y, and that means the output would be g into E, which is gx minus ghy. But we know this output is y. That is, we have gx minus ghy is equal to y. This allows us to solve for y in terms of x. So we have y, that is, if I take this side, we have gx is equal to y into 1 plus gh. Therefore we have y is equal to gx by 1 plus gh. And the absolutely fantastic part about this is another rational function. And what makes it even nicer is if you have a correspondingly nice transfer function for h, then if you have a correspondingly nice transfer function for h, Okay, we'll just write it explicitly. We'll write G is equal to numerator by denominator. So this is numerator by denominator by 1 plus num by denominator into a nice function. Provided this function is nice enough, we can simplify this into numerator by numerator into some number plus denominator. And therefore, to study this, it's almost sufficient to study G and H individually, and that makes the analysis of the entire thing incredibly nice. Another thing is, another thing is numerator. For example, if you're looking at, what's that thing called? Okay, so the only, yeah, so if you're looking at body plots, the important parts about body plots is the value 1 and the value 2 pi. Sorry, pi. An argument of pi and an argument of 1 and a magnitude of 1 is quite significant, in the sense, if your input is, say you have an input x, and then after this transfer function you're getting a magnitude of 1 and an argument of pi. An argument of pi means a negative number, and an argument of 1 means equal to the same magnitude. Therefore, if you have a specific transfer function whose magnitude is magnitude is not 1 here. By magnitude 1, you have to look at where the where the body plot intersects the x-axis. So in our case, the body plot intersects the x-axis at these ranges. So if the magnitude is 1 and the argument is pi, that means the transfer function inverts the signal. The transfer function will invert the signal, and if it inverts the signal, if you don't have a nice system, this inverted signal will just destructively interfere with the old signal, and this destructive interference with the old signal will therefore cause, it's not something we want. Therefore, with the if you're going to, therefore we can use the x-intercept of the magnitude and the and the point where the argument becomes 0 as kind of very important points, and we always draw vertical lines from those points to see where it intersects other thing. For example, I don't have MATLAB on my systems, but if you give me a second, maybe I do have MATLAB. Give me a second. Oh my god. So I can write a transfer function in MATLAB as follows. 1, 2, 3. A is equal to so essentially this MATLAB function generates a transfer function. So the inputs are 1 and 2 3. That means 1 will be the numerator and 2 3 will be the denominator. So if I had instead given 3 1, I'll get 3s plus this thing. So if I had taken the old one, I can take the body plot of this. Yeah. So what the okay, so it's because I'm using the online version, but if I had used the proper MATLAB version, it will tell me where the face margin and the two terms I just said are. Can I show? Let's but I can show the A is 1 1. But and here you can see what I just said. So here here we have a straight line. My God, give me a okay. So for the body plot of 1 by 1 plus s, as I said before, can you see my mouse cursor? It's right now near the 0 of phase degree. Okay. Okay, this is better, right? There should be a mouse cursor visible now. Okay, so for small frequencies, the phase will be very close to 0, and as it goes to 1, the moment it reaches 1, we get the phase becomes minus 45 degrees, and for higher values it becomes very close to minus 90 degrees. On the other hand, the magnitude plot is 0 throughout until it reaches 1, and after 1 it has a steady slope. So if I wanted to so I've multiplied with itself, and this time, while it's not clear, but the if you look at the magnitude, the range has changed and it's a steeper slope. Secondly, it now goes to minus 180 and not just minus 90. That's because naturally it has added it twice. Because when you add the two things to add the two plots twice, it will go from 0 to minus 180. Did that make sense? I don't think it did. Okay, so I will take a function. Ten comma 1. Okay, so let's look at the body plot of 10s plus 1 by 0.1 s plus 1. Before we do it, we'll just quickly solve it here. So it's 10s plus 1 by 0.1 s plus 1. So if you're looking at the magnitude plots, okay, we'll first look at 10s plus 1. 10s plus 1 will, give me a second, 10s plus 1 will go up or down? No, 10s plus 1 will go up, and it is it will, yeah, 10s plus 1 will go up, and it will, the the part where it starts going up is minus is at 0.1, because essentially over here the point where it the critical point is when the omega is equal to 1. So when you multiply by 1, we'll get when you reach 1, that's when the part where it splits. So 10s plus 1 will go, the plot of 10s plus 1 will be something like this. And if you look at the other plot, the plot of 0.1 s plus 1 will we can analyze it in the same way. So 0.1 s plus 1, the critical point is minus 10. So until minus 10 it's straight, and then it goes down. Note that it will go down with the same slope as this is going up. Likewise, the other, at 10 it will be here. So the blue is the body plot of the numerator, the red is the body plot of the denominator. Now we just have to add these. So when you add these, we get, when you add these, it first goes up, and then because this slope is equal to that slope, it will remain constant, I think. So we'll get, yeah, and for the argument, the slope will get, the graph will look like that. Let's check. Thank God. So as I said, at 0.1 this thing starts going up. At 10 the other one starts going down. So we get a hump shaped graph here. At 0.1 this starts picking up, the numerator starts picking up, and at 10 to the power 1 the denominator starts picking up, and therefore after 10 to the power 1 it will start flatlining. Yeah. So what I had done was, I first found the corresponding body plots of each of these, and then I added them, like how we just like adding two functions. If I'm honest, like, it takes practice by yourself to properly get a hang of this. If you do not have MATLAB, I guess Octave will have a similar function. Body plot in Octave. Yeah, Octave also has a body plot. So in case you want practice of drawing body plots, you can do it manually and then check the answer in MATLAB in Octave. So usually MATLAB is used in academic institutions, and if we have access to MATLAB, I don't know anybody who would use Octave but Octave is free. So if anybody outside the academy is using wants to play with matrices and body plots and the like, I guess they would use Octave. Since I'm not familiar with many people who use Octave instead of MATLAB, but that's because I do not know any people outside who's working specifically on body plots. Like in many cases, it's just more. Yeah, I do not know many people who use Octave, but I don't think that I do think many there are a niche set of people who use Octave. But MATLAB is just convenient enough, and I have MATLAB license, so yeah. MATLAB has an extremely powerful systems toolbox, which has a lot about Laplace transforms and all those. Laplace transforms, inverse Laplace transforms, and controls, transfer functions. So, like when I was learning this, we had to program a little bit in MATLAB to make sure we understood the concept. In addition to body plots, there's also a concept called Nyquist plots, which is also used for stability analysis. And yeah, essentially MATLAB is used for that also. So when I saw in the slides that that we have to study body plots again, that we are looking at body plots, I had to quickly go through everything, because every time I needed a body plot, I just used MATLAB. It's not too difficult. But I guess everything's that way. Like, if you practice enough, it is kind of second nature. Note that body plots and all were made before computers, and therefore many of these are for hand and you can just analyze it with your hands and a piece of paper. With the advent of computers, many things are significantly easier. Like, if I remember correctly, there's a function in MATLAB specifically for analyzing PID controllers. Yeah. So, is there any questions about this week's lectures? I'll quickly go over. We started with a recap as normal. We first saw there are ways to mathematically model the systems. So, and the important thing is, despite the various different equations we are using, they have a very similar form. So even though we're studying mechanical systems and electrical systems separately, in the end the mathematical model out of them is very similar, and studied how to studied how to solve these equations in the lecture 29, where we studied about dynamic response. The key takeaway of dynamic response is about the different order systems and how the total response and how to solve differential equations essentially. And then we come across transfer functions and frequency response and Bode plots in the last lecture, which is a more controls oriented way to solve these questions. Like for example, Laplace transform is significantly more convenient than using the equations, solving the equations normally using the normal ways we have solved ODEs. So we first solved a couple of questions on writing the modeling the equations. I will come back to this question next week, and we looked at this equation, looked at the undamped frequency and damping ratio, saw a lot of questions, and yeah, and then we conclude. So if there are, in 1 minute I will close the recording. Are there any specific questions about last week's class? If there are no more questions, I'll close the recording now. I will stay online for 5 more minutes.